Light can be described either as a wave or particle, depending on the circumstances under which it is observed. Module 5 looks at wave motion in general and specifically light as a wave. This will allow us to address a single competency, describe the properties of light, and apply them to solving simple optics problems. We will describe the particle nature of light in the last module. To talk about the wave nature of light, it is necessary to introduce the concept of waves. Chapter 15 covers more than a few concepts and definitions of terms related to waves in general. Waves come in different types, for example, longitudinal and transverse. Transverse waves are the type we think of in general when thinking of a wave. There is an up and down motion perpendicular to the direction of travel. Longitudinal waves have a back and forth motion in the direction of travel. Think about sending a series of pulses down a stretched out slinky, for example. Properties of waves such as wavelength, frequency, and wave speed are introduced. Phenomenon associated with waves such as reflection, refraction, superposition, interference, diffraction, and the Doppler effect are also introduced. In addition, Chapter 15 applies some of those concepts to sound and music. Sound waves would fall under the description of a longitudinal wave, while, as we will see later, light acts as a transverse wave. But all of the general definitions and concepts about waves can be applied to both sound waves and light waves. Chapter 16 delves into light proper. Here the concept of electromagnetic radiation is introduced, including the use of different wavelength bands. Depending on the size of the waves and the corresponding frequency, there are lots of different applications to different parts of the electromagnetic spectrum. Color is discussed, falling into two different categories, additive color mixing and subtractive color mixing. What colors we see depends on these characteristics. The product of the wavelength and frequency of a particular electromagnetic wave gives it speed, the speed of light. In a vacuum, it represents the fastest speed we know of. But when any electromagnetic wave passes through a physical medium, it is slowed. Properties of light waves include interference, diffraction, and polarization. Interference and diffraction were first covered in Chapter 15 when it came to mechanical waves, waves that need a medium to propagate through. Light is different in that it does not need a medium to move. It can move in a vacuum. Interference of waves can happen when light passes through thin slits, for example, leading to one of the experiments that clearly showed that light had a wave nature. But interference also occurs when light reflects off of parallel surface, say in the case of thin films of fluids, further demonstrating the wave nature of light. Diffraction can also be observed. Just as sound waves may bend as they pass through an open door, allowing one to hear even if not in direct line to the source, light waves do the same. Exploiting this wave property are objects known as diffraction gratings. Fine parallel lines etched on a reflecting surface or on a glass can break light up, diffract it. Under the right circumstances, it can separate colors of light much as a prism does. Polarization is related to the orientation of the transverse waves of light. Ordinary light may be oscillating back and forth in all sorts of directions compared to the direction of travel. Polarized light only oscillates in one direction, perpendicular to the forward motion of the light waves. Polarization can be achieved from reflection off of a flat surface or by passing light through appropriate filters. Polarization further demonstrates the wave nature of light. Chapter 17 further explores the wave nature of electromagnetic radiation, specifically looking at phenomena known as reflection and refraction. Reflection of waves deals with the energy of the wave when confined in the same medium. The law of reflection states that the angle made between the direction of the incoming radiation to the normal drawn perpendicular to a surface is the same as the angle of the direction of the outgoing or reflected radiation with respect to that same normal. Refraction, the bending of light when it moves from one medium to another, is used when explaining the apparent bending of an object seen in a glass of water or the sparkle of a diamond. Depending on the index of refraction of each medium, which is the ratio of the speed of light in a vacuum to the speed of light in that medium, the direction of the EM radiation can be changed. When going from a less optically dense medium to a more optically dense medium, the path is bent closer to the normal upon entry. But if the light source is in the denser medium, such that the light is moving toward a less dense medium, it becomes possible at the correct angle to trap the light within the more dense medium, what is known as total internal reflection. Plane mirrors can produce images referred to as virtual images. These are images that to our eyes seem to be there. The light is not actually passing through the image. For plane mirrors applying the law of reflection, one finds that the virtual image appears to be as far behind the mirror as the object providing the light is in front of the mirror. Things change when curvature is added to the reflecting surface. Mirrors can be bent inward or outward, and each type will produce different types of images. If a mirror is bent inward, say, in the shape of a partial surface of a sphere, then it is referred to as concave. If it is bent outward under the same conditions, say in the shape of a partial surface of a sphere, then it's referred to as convex. Depending on the type of mirror and the location of the object which produces the light, these mirrors can produce both virtual and real images. Real images are those through which the light actually passes, unlike virtual images mentioned earlier. These image production processes can also have broad application. Refraction can be exploited through the use of lenses. Like mirrors, the shape of the lens determines its type. Simple lenses that could be thought of as the outer partial surfaces of spheres are referred to as convex lenses. Those that can be thought of as the inner partial surfaces of spheres are referred to as concave lenses. And like spherical mirrors, spherical lenses can produce either virtual or real images, depending on the type of lens and the location of the light source. Chapter 17 continues with the application of lenses and mirrors in a variety of objects found today. The human eye uses a natural lens to produce images of objects in its surroundings onto the retina. Out of roundness can result in symptoms such as nearsightedness or farsightedness. Cameras can use both lenses and mirrors in the production of images, either collected on photographic emulsions or more recently on chips for electronic storage purposes. Microscopes can use lenses to be able to bring the small world into view to the human eye, and telescopes can reveal to the human eye the wonders of the universe, using lenses and or mirrors to gather and focus the light from those distant objects. Wave phenomenon is experienced all around us, whether it be the sound we hear from nearby traffic or the songs we hear from birds. The wave nature of sound helps explain what we hear. And the wave nature of light, from the scattering of light causing the blue skies, white puffy clouds, the colors of the rainbow, or the simple ability to see all of that, explains numerous phenomena we can observe with our eyes or other electromagnetic detection devices. Module 5 attempts to address much of this.